Examples of machine learning applications. Learning associations. In the case of retail, for example, a supermarket chain, one application of machine learning is basket analysis, which is finding associations between products bought by customers. If people who buy X typically also buy Y, and if there is a customer who buys X and does not buy Y, he or she is a potential Y customer. Once we find such customers, we can target them for cross-selling. In finding an association rule, we are interested in learning a conditional probability of the form P of Y conditioning on X, where Y is the product we would like to condition on X, which is the product or the set of products which we know that the customer has already purchased. Let us say, going over our data, we calculate that P, the probability of chips conditioning on beer, is equals to 0.7. Then we can define the rule. 70% of customers who buy beer also buy chips. We may want to make a distinction among customers, and toward this, estimate the probability of Y conditioning on X D, where D is the set of customer attributes. For example, gender, age, marital status, and so on, assuming that we have access to this information. If this is a bookseller instead of a supermarket, products can be books or authors. In the case of a web portal, items correspond to links to web pages, and we can estimate the links a user is likely to click and use this information to download such pages in advance for faster access. Classification. A credit is an amount of money loaned by a financial institution, for example a bank, to be paid back with interest, generally in installments. It is important for the bank to be able to predict in advance the risk associated with a loan, which is the probability that the customer will default and not pay the whole amount back. This is both to make sure that the bank will make a profit and also to not inconvenience a customer with a loan over his or her financial capacity. In credit scoring, Hand 1998, the bank calculates the risk given the amount of credit and the information about the customer. The information about the customer includes data we have access to and is relevant in calculating his or her financial capacity, namely income, savings, collaterals, profession, age, past financial history, and so forth. The bank has a record of past loans containing such customer data and whether the loan was paid back or not. From this data of particular applications, the aim is to infer a general rule coding the association between a customer's attributes and his risk. That is, the machine learning system feeds a model to the past data to be able to calculate the risk for a new application and then decides to accept or refuse it accordingly. So this is an example of classification problems where there are two classes: low risk and high risk customers. The information about a customer makes up the input to the classifier, whose task is to assign the input to one of the two classes. After training with the past data, a classification rule learned may be of the form: if income is greater than theta 1 and savings is greater than theta 2, then low risk, else high risk. For suitable values of theta 1 and theta 2, see figure 1.1, this is an example of a discriminant. It is a function that separates the examples of different classes. Having a rule like this, the main application is prediction. Once we have a rule that fits the past data, if the future is similar to the past, then we can make correct predictions for novel instances. Given a new application with a certain income and savings, we can easily decide whether it is low risk or high risk. In some cases, instead of making a 0-1 low risk over high risk type decision, we may want to calculate a probability, namely P of y conditioning on x, where x are the customer attributes and y is 0 or 1 respectively for low risk. And high risk. From this perspective, we can see classification as learning and association from X to Y. Then, for a given capital X equals to little x, if we have the probability that capital Y is equals to 1, conditioning on capital X is equals to X is equals to 0.8, we say that the customer has an 80% probability of being high risk, or equivalently, a 20% probability of being low risk. We then decide whether to accept or refuse the loan depending on the possible gain and loss. There are many applications of machine learning in pattern recognition. One is optical character recognition, which is recognizing character codes from their images. This is an example where there are multiple classes, as many as there are characters we would like to recognize. Especially interesting is the case when the characters are handwritten, for example, to read zip codes on envelopes or amounts on checks. People have different handwriting styles. Characters may be written small, large, slanted with a pen or pencil, and there are many possible images corresponding to the same character. Though writing is a human invention, we do not have any system that is as accurate as a human reader. We do not have a formal description of A that covers all A's and none of the non-A's. Not having it, we take samples from writers and learn a definition of A-ness from these examples. But though we do not know what it is that makes an image an A, we are certain that all those distinct A's have something in common, which is what we want to extract from the examples. We know that a character image is not just a collection of random dots. It is a collection of strokes and has a regularity that we can capture by a learning program. If we are reading a text, one factor we can make use of is the redundancy in human languages. A word is a sequence of characters, and the successive characters are not independent but are constrained by the words of the language. This has the advantage that even if we cannot recognize a character, we can still read the word. Such contextual dependencies may also occur in higher levels between words and sentences through the syntax and the semantics of the language. There are machine learning algorithms to learn sequences and model such dependencies. In the case of face recognition, the input is an image. The classes are people to be recognized, and the learning program should learn to associate the face images to identities. This problem is more difficult than optical character recognition because there are more classes. Input image is larger and the face is three-dimensional, and the differences in pose and lighting cause significant changes in the image. There may also be occlusion of certain inputs. For example, glasses may hide the eyes and the eyebrows, and a beard may hide the chin. In medical diagnosis, the inputs are the relevant information we have about the patient, and the classes are the illnesses. The inputs contain the patient's age, gender, past medical history, and current symptoms. Some tests may not have been applied to the patient, and thus these inputs would be missing. Tests take time, may be costly, and may inconvenience the patient, so we do not want to apply them unless we believe that they will give us valuable information. In the case of a medical diagnosis, a wrong decision may lead to a wrong or no treatment, and in cases of doubt, it is preferable that the classifier reject and defer decision to a human expert. In speech recognition, the input is acoustic and the classes are words that can be altered. This time, the association to be learned is from an acoustic signal to a word of some language. Different people because of differences in age, gender, or accent pronounce the same word differently, which makes this task rather difficult. Another difference of speech is that the input is temporal. Words are altered in time as a sequence of speech phonemes, and some words are longer than others. Acoustic information only helps up to a certain point, and as in optical character recognition, the integration of a language model is critical in speech recognition, and the best way to come up with a language model is again by learning it from some large corpus of example data. The applications of machine learning to natural language processing is constantly increasing. Spam filtering is one where spam generators on one side and filters on the other side keep finding more and more ingenious ways to outdo each other. Perhaps the most impressive would be machine translation. After decades of research on hand-coded translation rules, it has become apparent recently that the most promising way is to provide a very large number of example pairs of translated texts and have a program figure out automatically the rules to map one stream of characters to another. Biometrics recognition or authentication of people using their physiological and or behavioral characteristics that requires an integration of inputs from different modalities. Examples of physiological characteristics are images of the face, fingerprint, iris, and palm. Examples of behavioral characteristics are dynamics of signature, voice, gait, and keystroke. As opposed to usual identification procedures, photo, printed signature, or password, when there are many different uncorrelated inputs, forgeries like spoofing would be more difficult and the system would be more accurate, hopefully without too much inconvenience to the users. Machine learning is used both in the separate recognizers for these different modalities and in a combination of their decisions to get an overall accept or reject decision, taking into account how reliable these different sources are. Learning a rule from data also allows knowledge extraction. The rule is a simple method that explains the data, and looking at this model, we have an explanation about the process underlying the data. For example, once we learn the discriminant separating low-risk and high-risk customers, we have the knowledge of the properties of low-risk customers. We can then use the information to target potential low-risk customers more efficiently, for example, through advertising. Learning also performs compression in that by fitting rule to the data, we get an explanation that is simpler than the data, requiring less memory to store and less computation to process. Once you have the rule of addition, you do not need to remember the sum of every possible pair of numbers. So another use of machine learning is outlier detection, which is finding the instances that do not obey the rule and are exceptions. In this case, after learning the rule, we are not interested in the rule, but the exceptions not covered by the rule, which may imply anomalies requiring attention, for example, fraud. Regression. Let us say we want to have a system that can predict the price of a used car. Inputs are the car attributes, brand, year, engine capacity, mileage, and other information that we believe affect a car's worth. The output is the price of the car. Such problems where the output is a number are regression problems. Let X denote the car attributes and Y be the price of the car. Again, surveying the past transactions, one can collect a training data and the machine learning program feeds a function to this data to learn Y as a function of X. An example is given in figure 1.2 where the fitted function is of the form y equals to wx plus wo for suitable values of w and wo. Both regression and classification are supervised learning problems where there is an input x and output y, and the task is to learn the mapping from the input to the output. The approach in the machine learning is that we assume a model defined up to a set of parameters, that is y equals to g of x conditioning on theta, where g dot is the model and theta are its parameters. Y is a number in a regression and is a class code. For example, 0 or 1 in the case of classification. G dot is the regression function, or in a classification, it is the discriminant function separating the instances of different classes. The machine learning program optimizes the parameters theta such that the approximation error is minimized, that is, our estimates are as close as possible to the correct values given in the training set. For example, in figure 1.2, the model is linear and W and WO are the parameters optimized for best fit. 2. The training data. In cases where the linear model is too restrictive, we can use for example, a quadratic. Y equals to W2 times x squared plus W1 times x plus W0, or a higher order polynomial, or any other non-linear functions of the input, thus optimizing its parameters for best fit. Another example of regression is navigation of a mobile robot, for example, an autonomous car, where the output is the angle by which the steering wheel should be turned at each time to advance without hitting obstacles and deviating from the route. Inputs in such a case are provided by sensors on the car, for example, a video camera, GPS, and so forth. Training data can be collected by monitoring and recording the actions of a human driver. One can envisage the other applications of regression where one is trying to optimize a function. Let us say we want to build a machine that roasts coffee. The machine has many inputs that affect the quality, various settings of temperatures times coffee bean type. And so first we make a number of experiments, and for different settings of these inputs, we measure the quality of the coffee, for example, as consumer satisfaction. To find the optimal setting, we fit a regression model linking these inputs to coffee quality and choose new points to sample near the optimum of the current model to look for a better configuration. We sample these points, check quality, and add these to the data and feed a new model. This is generally called response surface design. Unsupervised learning. In supervised learning, the aim is to learn a mapping from the input to an output whose correct values are provided by a supervisor. In unsupervised learning, there is no such supervisor and we only have input data. The aim is to find the regularities in the input. There is a structure to the input space such that certain patterns occur more often than others, and we want to see what generally happens and what does not. In statistics, this is called a density estimation. One method for density estimation is clustering, where the aim is to find clusters or groupings of input. In the case of a company with the data of past customers, the customer data contains the demographic information as well as the past transaction with the company, and the company may want to see the distribution of the profile of its customers to see what type of customers frequently occur. In such a case, a clustering model allocates customers similar in their attributes to the same group, providing the company with a natural groupings of its customers. This is called customer segmentation. Once such groups are found, the company may decide strategies, for example, services and products specific to different groups. This is known as customer relationship management. Such a grouping also allows identifying those who are outliers, namely those who are different from other customers, which may imply a niche in the market that can be further exploited by the company. An interesting application of clustering is in image compression. In this case, the input instance are image pixels represented as RGB values. Clustering program groups pixels with similar colors in the same group, and such groups correspond to the colors occurring frequently in the image. If in an image there are only shades of a small number of colors, and if we code those belonging to the same group with each other, for example, their average, then the image is quantized. Let us say the pixels are 24 bits to represent 16 million colors, but if there are shades of only 64 main colors, for each pixel we need 6 bits instead of 24. For example, if the scene has various shades of blue in different parts of the image, and if we use the same average blue for all of them, we lose the detail in the image but gain space in the storage and the transmission. Ideally, one would like to identify higher level regularities by analyzing repeated image patterns, for example, textures, objects, and so forth. This allows a higher level, simpler, and more useful description of the scene, and, for example, achieves a better compression than compressing at the pixel level. If we have scanned the document pages, we do not have random on-off pixels, but bitmap images of characters. There is a structure in the data, and we make use of this redundancy by finding a shorter description of the data. 16 times 16 bitmap of A takes 32 bytes. Its ASC2 code is only 1 byte. In document clustering, the aim is to group similar documents. For example, news reports can be subdivided as those related to politics, sports, fashion, arts, and so on. Commonly, a document is represented as a bag of words That is, we predefine a lexicon of n words, and each document is an n-dimensional binary vector whose element I is one if word I appears in the document. Suffixes s and ing are removed to avoid duplicates. In words such as of and so forth, which are not informative, are not used. Documents are then grouped depending on the number of shared words. It is of course here critical how the lexicon is chosen. Machine learning methods are also used in bioinformatics. DNA in our genome is the blueprint of life and is a sequence of bases, namely A, G, C, and T. RNA is transcribed from DNA, and the proteins are translated from the RNA. Proteins are what the living body is and does, just as a DNA is a sequence of bases. A protein is a sequence of amino acids as defined by bases. One application area of computer science in molecular biology is alignment, which is matching one sequence to another. This is a difficult string matching problem because strings may be quite long. There are many, and there are many template streams to match against, and there may be deletions, insertions, and substitutions. Clustering is used in learning motifs which are of interest because they may occur to structural or functional. Elements within the sequence they characterize. The analogy is that if the amino acids are letters and proteins are sentences, motifs are like words, namely a stream of letters with a particular meaning occurring frequently in different sentences. Reinforcement learning. In some applications, the output of the system is a sequence of actions. In such a case, a single action is not important. What is important is the policy, that is, the sequence of correct actions. To reach the goal, there is no such thing as the best action in any intermediate state. An action is good if it is part of a good policy. In such a case, the machine learning program should be able to assess the goodness of policies and learn from past good action sequences to be able to generate a policy. Such learning methods are called reinforcement learning algorithms. A good example is game playing, where a single move by itself is not that important. It is the sequence of right moves that is good. A move is good if it is part of a good game playing policy. Game playing is an important research area in both artificial intelligence and machine learning. This is because games are easy to describe and at the same time they are quite difficult to play well. A game like chess has a small number of rules, but it is very complex because of the large number of possible moves at each side and the large number of moves that a game contains. Once we have good algorithms that can learn to play games well, we can also apply them to applications with more evident economic utility. A robot navigating in an environment in search of a goal location is another application area of reinforcement learning. At any time, the robot can move in one of number of directions. After a number of trial runs, you should learn the correct sequence of actions to reach to the goal state from the initial state, doing this as quickly as possible and without hitting any of the obstacles. One factor that makes reinforcement learning harder is when the system has unreliable and partial sensory information. For example, a robot equipped with a video camera has incomplete information, and thus, at any time it is in a partially observable state, it should decide to take into account this uncertainty. For example, it may not know its exact location in a room, but only that there is a wall to its left. A task may also require a concurrent operation of multiple agents that should intersect and cooperate to accomplish a common goal. An example is a team of robots playing soccer.